All right, let's do one more example that looks at projectile motion. This one's going to be a little bit more tricky. Okay, so in a children's story, a princess trapped in a castle wraps a message around a rock and throws it from the top of the castle. Right next to the castle is a moat. The initial velocity of the rock is 12 meters per second at an angle of 42 degrees above the horizontal. The rock lands directly on the other side of the moat at a level of 9.5 meters below the initial level. Air resistance is negligible. So a lot like the last problem, they want us to calculate the rock's time of flight, calculate the width of the moat, and we are going to make a little assumption for that one, and then determine the rock's velocity on impact with the ground. Okay, so I am going to start by drawing out this situation here. Okay. So what we have is some ground. On that ground, we have our castle. Okay, our princess is standing on the top of that castle. Okay, and then what we have is basically what we're assuming is that's right directly surrounding the edge of this castle is a moat that wraps around like this. Okay, so we have some moat. Okay, she is then throwing this rock. If I draw a dotted line with the horizontal here, she is throwing this rock. Okay, my angle's a little bit crude here, but she's throwing it at an angle of 42 degrees at 12 meters per second. It's going to go up. And basically, we're assuming that it just clears the side of the moat and lands right here. Okay, and that's what's going to allow us to determine the width of the moat for B. Okay, but then we also know the last piece of information is that the height that she is above the ground is 9.5 meters. Okay, so she's throwing a rock. It's going up, coming down, and landing directly on the other side of the moat. Okay, and that's the assumption that we're making here. Okay, now we can go and do what we always do in terms of projectile motion problems, is we're going to break down our variables into those x and y components. Okay, so let's always start with the initial velocity. So with the initial velocity, well, we have an angle here that's been given above the horizontal, so we are going to have to find those components of the initial velocity. Oops, sorry. And the initial velocity in the x direction is going to be equal to the magnitude of that initial velocity times, remember with projectile motion, the x is always going to be related to the cos of the angle that they give you. Okay, so we're taking 12 meters per second and multiplying by the cos of 42 degrees to get our initial velocity in that x direction. And we get 8.918 meters per second. And we do the same thing in the y direction. Only difference now is we take that initial velocity and multiply it by the sine of the angle to find that y component. So again, your 12 meters per second gets multiplied by the sine of 42 degrees. Okay, and that's going to give us 8.029 meters per second. Okay. And actually, let's take this one more further too. We'll do 8.9177 meters per second. Okay. Then, next thing we always know is that acceleration in both directions. We always know that the acceleration in the x direction is 0, and the acceleration in that y direction is our negative 9.8 meters per second squared. Okay. Last thing that we've been given in the problem is the displacement of the stone. We know that the displacement of the stone is negative 9.5 meters, right? Because it lands 9.5 meters below the initial starting point. Okay, so we're going to use again the y direction to find that time. Okay, so to find the time, a lot like we did in problem 1.5.1, we're going to use that exact same kinematic equation that says the displacement is equal to the initial velocity times time plus 1/2 that acceleration times time squared. Okay. Unfortunately, this time we have all of these variables. Okay, so what we're going to have to do in this case is we're going to plug everything in. Okay, and you'll notice what we have here is a quadratic with time as the variable that we're looking for. Okay, so I'm going to rearrange to have 0 on the one side of the equation, and I'm just going to rearrange so it actually looks like a quadratic. Means I have negative 4.9. I'm also just going to drop the units in this case, so I have negative 4.9 times time squared plus 8.0296 times time plus 9.5. Okay, now we can go ahead and use our quadratic equation, right? Where negative 4.9 is our A value, positive 8.0296 is our B value, and 9.5 is our C value. Okay, so the quadratic equation says that time is going to be equal to negative b plus or minus the square root of b squared minus 4ac all over 2 times a. Okay, so we get negative 8.0296 plus or minus the square root of 8.0296 squared minus 4 times negative 4.9 times 9.5. Sorry, just couldn't remember if it was positive or negative there, and it's positive because we moved it over to that other side of the equation. Okay, that's all square rooted, and then that gets divided by 2 times negative 4.9. So we're going to simplify. We get negative 8.0, oops, 296 plus or minus, this works out to be 64.4745 plus becomes plus because we have negative times negative, plus 186.2 all over negative 9.8. We get negative 8.0296 plus or minus the square root of 250.6745 all over negative 9.8, which means we end up with negative 8.0296 plus or minus 15.8327 all divided by negative 9.8. Okay, now we can go and do the plus and the minus, right? Now, if we look up here at the plus, okay, we have negative 8.0296 plus 15.8327 divided by a negative number, right? So if we have a positive divided by a negative, this is going to give us a negative time, which we can't have. So we're simply just going to ignore that one based on that fact, okay? And we're just going to go and look at the minus. So I get negative 8.0296 minus 15.8327 divided by negative 9.8. Okay, that's going to give me that gives me 2.4349 seconds. Okay, so therefore the time that it takes for the rock to hit the ground is 2.4 seconds if we go to our significant figures. Okay, and if you look at the picture, it also makes sense if you think about why we only have one positive time, right? This is technically a parabola, so if we continue this backwards, what you're actually finding is that other zero over here, right? And in terms of our situation, right here is where time equals 0, and that's why we can't have a negative time in this case. Okay? Next, part B asks us to solve for the width of the moat. And because we're assuming that the rock landed right on the other side of the moat, technically what we're going to try to look for then is the displacement in the x direction. Okay? And remember, because of the variables we have, we're now using the exact same equation again. Only difference is we're now using it in the x direction. And beauty is we always know the acceleration in that x direction is 0. So the displacement is simply going to be equal to the initial velocity in that x direction, which was 8.9177 multiplied by our time of 2.4349 seconds. Okay, and that's going to give us a displacement of 21.714 meters. So therefore, the displacement in the x direction, or the width of the moat, is going to be 22 meters. Okay, should probably put a direction in here. I know they didn't give us one, so we'll just call it forward. Okay, and then last but not least, they do want us to solve for that final velocity that the rock hits the ground with. Okay, so remember, because there is no acceleration in the x direction, that final velocity is equal to that initial velocity in the x direction. So we already know that the final velocity is 8.9177 meters per second in the x direction. And then for the y direction, we're using our formula that says Vfy squared is going to be equal to the initial velocity in the y direction squared plus 2 times the acceleration in the y direction times the displacement in the y direction. Okay, so when we go and solve for the final velocity in the y direction, we're literally just taking the square root of all these. So the initial velocity in the y direction was that 8.0296 meters per second squared plus 2 times acceleration, which is negative 9.8 meters per second squared, times negative 9.5 meters. Okay, gives me 64.4740 plus 8. So the final velocity in the y direction comes out to 15.8327 meters per second. Okay, so now you have your final in the y, you have your final in the x, and we can start by putting them together. So the magnitude of our final velocity is the square root of final velocity in the x direction squared plus the final velocity in the y direction squared. So in the x direction, it was that 8.9177. In the y direction, that was what we just solved for, that 15.8327. Okay. Square those two values and add them together. And we get 330.1994 meters squared per second squared, which means that our final answer, if we take the square root of that, is 18.17 meters per second. Okay, then we need to find that angle. So to find it compared to the horizontal, you're doing VF in the y direction over VF in the x direction. Okay, so we're taking the tan inverse of 15.8327 divided by 8.9177. Okay. And I get an answer of 60.61 degrees. So therefore, the final velocity that our rock hits the ground with is 18 meters per second at an angle of 61 degrees below the horizontal. Okay, And that's it for projectile motion day one.